Hey everybody, today I'd like to talk about how Microsoft engineers were able to revamp TCP, which is a fundamental protocol. And I'd like to do this as if we were the Microsoft engineers. So we're going to go over the problem and how we can use our deep understanding of network architecture in order to build the solution ourselves. And this will show you how innovation is possible, even in networks, and why a deep understanding of the headers and the control bits and all the different algorithms is actually really useful, especially in niche cases like this. Microsoft is a massive company and they have massive data centers. And when these machines want to talk to each other, they'll send data. And what the Microsoft engineers discovered was that they were having some problems. Firstly, they had a high latency and a low bandwidth. So they decided to diagnose this problem and they drew up this graph, which will show us that the traffic is bursty, which explains the low bandwidth utilization, like here, and the high latency, because there's peaks where it floods the network with data, and then not all of it is processed immediately. So it'll have to wait to get the ACK responses. As humans, we can imagine the lines to be more like this, more flat, just like these edges over here. So let's try and think about what could be causing this problem. And here's a hint. It's the protocol they're using. Imagine these are two machines in a Microsoft data center. You got the sender and you have the receiver. So the sender will send packets to intermediary nodes, but an intermediary node could actually have multiple endpoints. It doesn't just have to be these two. And so it can have lots and lots of packets building up. And the goal is to get them to their destination. But it's not able to process all of these at the same speed. So it will start to store these in a queue. Let's say the queue size is 3, not massive. So the first one's added to the queue while the current one's being processed. If another one comes in, it's added to the queue. And the third one is added to the queue as well. But what if a fourth packet comes in? Well, there's no space for it in the queue, so we have to drop it. And this is packet loss. Now, TCP already has a way for dealing with packet loss, and that is congestion control. The mechanism for that is additive increase, multiplicative decrease, which if we applied on a graph would be the maximum bandwidth being somewhere around here. I'll call it M, and then it will slowly probe for a higher and higher bandwidth, reaching the maximum, then going slightly beyond that, experiencing that packet loss, and then halving its rate, the multiplicative decrease. And then it will additively increase again, and decrease, and increase, and decrease. Does this look familiar? It's actually a clear explanation of why that graph at the start was so bursty, and therefore we have now found the problem, which is causing our high latency and low utilization, because here we aren't near the maximum throughput, and yet we have to go through this point in order to reach the top. We can either change the congestion control, or we can think of some other mechanism. And if we come back to our diagram where we found the problem, we can intuitively think about what's causing the problem, and it's the queuing here. So the current algorithm is reactive. It waits for the packet loss to be detected before it does anything. But what if we never let the packet be dropped in the first place? What if, say, after the queue becoming 2/3 full, 2 out of the 3 packets being in the queue, we send a message from the congested router to the receiver that, hey, I'm experiencing congestion experienced, or an acronym that's CE. But the receiver can't do anything about it. So this will forward that message back to the sender, and that would be our congestion signal. And so the sender would then decrease its rate, and this would be a more proactive approach rather than being reactive. And this feature is already built into the TCP IP stack. It's called ECN, Explicit Congestion Notification Support. So the IP header contains these ECT bits, which simply says that we will be participating in this protocol. So it's set to 01, saying that we will be passing on this signal. And then when a router experiences congestion, it will change those bits in the IP header to 1, signifying that I am congested, and then forward these to the receiver. The next time the receiver sends an ACK packet, it will mark in its TCP header that it had received this congestion experience notification. This ACK packet will reach the sender where it is able to handle its bandwidth and throughput, reducing that. And in congestion control, it halves it, but we'll see just how the Microsoft engineers did that. Let's recall the point of TCP is to provide a reliable connection. And so when we send that ACK packet, the network is still congested. We haven't reacted to it yet. So how can we guarantee that the ACK packet will get there? And this state diagram is taken from the Microsoft paper explaining how they've implemented this better version of TCP. And it explains that we will keep sending an ACK packet every M packets received with the notification set until the sender tells us somehow that it has indeed reduced its window size. Let's look at exactly where these messages are inside of the packets. So in a TCP handshake, we can recall that the three-way handshake involves a sync ACK, and an ACK. And these flags are set inside of the header. We can see the ACK and the sync here. And we can also see these two flags. Zoning in on them, these are the congestion window reduced flag, which is sent by the sender once it has reduced its size, and the ECE echo flag, which is marked by the receiver to signify to the sender to reduce its window size. Now, how did the Microsoft engineers interpret these marked packets at the sender, rather than just halving the rate, which we know might not be as effective? We can think that if I have received 4 different ACK packets and none of them have the congestion notification set, and if I receive a new packet where it is set, then the congestion in the network probably isn't that high. Whereas if I received 4 packets where it is set and the last one isn't set, then there may still be congestion, even though the most recent packet is telling me that it isn't that high. And that's what this variable a keeps track of for us. It assigns a weight to the newest one, and it also assigns a weight to the previous value of a. And because of that, we're sort of maintaining an exponential weighting to each value in the bit stream of ECN packets, if that means anything to you guys. And thinking about what we do to the bandwidth, well, we can reduce our sending window by a factor of 1 minus alpha over 2. So in the worst case, where all we have received is ones in our ECN bits, then we would in fact half the window size. And if we have received only zeros, then the value of this would be 0, and so we wouldn't change the window size at all. So the Microsoft engineers and us have now been able to turn a single bit into a stream of information, which keeps track about how the congestion in the network was and update that with new information. So let's see how effective it actually was. As we can see from the diagram, which we've seen before, the TCP packets produce very bursty data, whereas using DC TCP, which is the name of the protocol that the Microsoft engineers created, is a lot more smooth, as we expect. So thank you very much for watching this video, and I hope you learned something.